All right, this is the last part on chapter 2 for No Nonsense Quantum Field Theory. Again, this is a really good book. It summarizes a lot of stuff really nicely, I think. And so let's get right into this. So we're talking about, I think it's like 2.6 now in the book, where we're talking about Lorentz and Poincaré transformations. A Lorentz transformation has to do with rotations of 4 vectors in spacetime, and a Poincaré transformation is a combination of rotations and a boost in spacetime as well. And so I'll write that down, but for the majority of this section, which is 2.6, so Lorentz transformation and Poincaré transformation again, Lorentz transformations have to do with rotations that I spelled that wrong, rotations. And Poincaré transformations have to do with rotations plus transformations. And this section of the book really isn't a deep dive into Lorentz and Poincaré transformations, but it does give some of the more relevant and physical examples of what some of these rotations and transformations might look like. So the main idea here is that we want to find rotation vectors and rotation matrices and boost matrices that preserve the structure of space-time when we transform these vectors. So we want to be able to transform the vectors, but be able to have the Minkowski metric work on these vectors even when they're transformed. And we also want them to look like something relevant, something that could be a reasonable physical transformed vector, right? And so the rotations, in the book, he just kind of gives the matrices. He doesn't derive them. And we're not going to derive them here because it'll take a while, I think. I think it'll take a while to derive these matrices. And in the book, he says the same thing. You can find the derivations for these matrices in his other book, which is called Physics from Symmetry. And I do want to go over that book. That's a very interesting book. Nevertheless, however, we're going to stick with just what he gives us for right now, and we'll derive those matrices later when we go over that book. Anyways, here's our rotation matrices. So this is a rotation matrix in the x plane. So we're rotating in the x plane. And you could see we have this here. This is what our typical two-dimensional transformation looks like. And then we have these 2 added dimensions to our matrix. And that's really what this rotation is. So we could take a 4 vector and we can rotate it, right? We can rotate this 4 vector, and we can rotate a 4 vector with this matrix. And what that would look like, if I write this out, is if we could have our mu nu rotation in the x direction. Typically this subscript here doesn't have to be written down. I'll just say x. in the x plane, sorry, times some vector a mu, right? And that's going to be equal to, well, this isn't really a tensor, so we'll just say a mu. That's going to be equal to a nu prime. So the prime means this is the new rotated vector. So we apply the rotation to an old vector to get a new vector, right? And we can do this with any of these matrices. We can rotate in the y-plane, right? So if we rotate in the y-plane, this is our y. It looks like an x, but that's a y. We're rotating our 4 vector in the y-plane, looks like this, okay? And then to rotate our 4 vector in the z-plane, we use this matrix, okay? And then we can say, well, we have boosts also, so we can rotate in x and y and z. We can also boost in x, y, and z, right? So when we boost in x, y, and z, we're using these matrices here, which can also be derived, where gamma of mu is something we've talked about already. So gamma of mu is merely just that factor, the Lorentz factor, the 1 over the square root of 1 minus u squared over c squared. And the beta of mu is equal to mu over c, okay? So we can rewrite gamma of u, right? This is a function of velocity. The u is the velocity of the particle. We can rewrite it as 1 minus u squared, or beta, or b of mu, or beta of mu squared. So we can rewrite, so gamma is in this case a function of beta, right? Because we have our beta in the function, but we don't have to. The beta is merely just this squared, which is right here, right? So we can, so that's what these guys are in here, in these entries. So we can boost in the x direction, we can boost in the y direction, and we can boost in the z direction. Now, in the book, he goes through an example on what these, how these beta matrices, or how rotation in the x direction, or in the x plane, preserves the metric, preserves the Minkowski metric. Let's do that for a boost, right? So we could just see as another example how these matrices work in preserving a metric. So what I'm going to do is I'm just going to rewrite. Let's boost our particle in the x direction. So what I'm going to do is I'm just going to take this boost in the x direction. I'm going to copy it. And let's go to a new page and paste it, just to remind us what this boost looks like. What we want to do is, if we recall delta S, we recall that this is some 4 vector, right? C delta t, x, y, and z, with negative signs on there. Times C delta t, x, y, and z. When we multiply those out, we're going to get c squared delta t squared minus, we should put deltas in front of those. Right? So I'm just going to put the deltas in front of those. The spatial components right here. Delta x squared minus delta y squared minus delta z squared. All right, so we have, again, these minus signs, which is what we're looking for. So now, and if we remember that this here, this is a mu, and this is also, this is also a mu, but it's a mu as a covector, as a different vector, because this is the transformed, right? This one is the transformed vector. And when we do that transformation, remember, we lower the index. Right, so we want to, so essentially what delta S is, in terms of A, is a mu, like that. Well, if we want to preserve, so a mu, let's say a mu prime is a newly transformed vector, and a mu prime is that newly transformed vector, right? So we are taking a newly transformed vector and performing an inner product with itself, and we're noting that that should stay as an invariant quantity, right? And it should also preserve this sort of structure where we have, let me double check, I just want to make sure I'm doing this right, where we have that, this is the same thing, as a mu prime times our Minkowski metric mu nu a nu, like that. Right. Okay. So now what we want to do is we want to rotate this guy. We can rotate this guy, and we can rotate this guy right here. So to do that, in the book, again, the book is using the a rotation matrix, but we want to use, let's use our beta matrix, or our boost matrix. So to use the boost matrix, we do gamma mu. Let's see, I'm just going to copy this just so that I can save some time. I just want to go through one example here. Okay. So what we're going to have is, let's see, I'm actually going to draw this out first. So what we're going to have, let's write out our rotation, this in our sort of rotation form, where we're going to have, so we're going to say that a mu, is the same thing as a sigma times the rotation, or a boost, actually, we're doing a boost, times a boost mu sigma, right? So we're getting rid of the sigmas and we're contracting back to the u. That's a rotated vector. And then a mu, or a nu here, is going to be beta, we can do we actually want this to be mu because we're contracting over the lower index of the Minkowski metric. We always want to make sure these indices are in check. And this will be, let's say, gamma nu. No, my bad. This will be, let's see. In the book example, they label this as a row, so I'll just do a row also. Do a row, and we want to rotate that, or not rotate it, we want to boost it as mu rho a rho, like that. Okay, I just want to make sure I got the indices good. Sometimes my head can mix those up a little bit, but anyways. So what we have now is, let's clean this up a little bit, a rho times b nu rho times gamma of mu nu times b nu rho times a rho. So I did in this right here, I just moved them around because one's just a vector. You can move that around. If this was a matrix, which it wouldn't be, but if it was, you couldn't just do that swap because matrices do not obey that commutation rule. So what we can do now is we can say that this is equal to a, that should not be a row, or that should be a row right here actually. Oops, like that. So a, like that, and then let's paste. Okay, why isn't this pasting? I'm gonna try to copy it again. Select, we're gonna paste this, copy it, copy, and paste. Right, and then I can erase this. There we go. And then I'll just move this down here, make it look a little bit better. And then we have our Minkowski metric, which is just 1, -1, -1, -1, 0, 0, 0, 0, 0. Just put zeros everywhere. That, and then we have our other rotation matrix, or our boost matrix. I'm going to have to copy it again. Copy. And paste. There we go. And then our last thing we want to put in here is our A row. A row, like that. All right, so this takes up a lot of space here. So let's do this one first. Let's do this multiplication first, where we're going to just do these two matrices. Right, so if we did that, we're going to be doing this. So this times this. Right, so that's just going to extract this guy. Everything else is going to be 0. So that's just going to be gamma mu. Gamma of mu, oops. Gamma of mu, and mu looks like a W. There we go. And then we're going to do, so that was this times this, right? So it's going to, so this times this plus this times this plus this, and so on. Then we want to do this one times this one, right? So that's going to be, again, that's just going to extract our gamma mu of mu times beta of u, right? And then we're going to do a race, or not a race, we want a point. I'm going to do this times this one, and that's going to be, again, that's just going to be zeros all over the place. And then this one times the last one, that's just going to be zeros, right? We can do the same thing now, and what I'm going to do is I'm just going to multiply everything out and then restart the video so that this doesn't take too much time on you guys. And so I'll come back within a minute here, and yeah. All right, so what I've done is I've just sped up the process a little bit so that we're not going through tedious matrix multiplication here. But what you'll be able to see here now is that when we multiply these two vectors together, we get this, okay? And then when we get, once we get this, then we can bring this up. I brought it up here. It's the same matrix, and then this is that third matrix. This is this one right here, okay? So what we end up with now is this expression, and this is equal to a mu, that's the rotated, or the newly rotated vectors and their components. And so we can do this matrix multiplication remembering the fact that when we get something like this, right, we can factor out gamma squared, right, and we have to get something like this. And then gamma squared is, if you remember, 1 over beta squared, and so that's going to end up being 1. Also, we want to keep in mind that this here, we're going to get expressions that look like this also. This can be 0, right? Because this is just the negative of that. So this is 0. So keeping those in mind, we'll be able, again, this is just an example. You can do the rest for yourself if you want, but you'll be able to find this expression right here. This isn't like an equation to remember or anything like that, but this is just to say that our newly rotated vectors look the exact same. They preserve this Minkowski metric, right? So our boost vectors, or our boost matrices, and our rotation matrices preserve this metric when we try to find these invariant delta S quantities, if you will, or when we do a dot product, right? When we do a dot product between two 4 vectors that live in space-time, we have now been able to find the rotations and the boosts that preserve the structure of that space-time, which is given to us by the Minkowski metric. And again, the Minkowski metric is a metric, or a matrix, that looks like 1 in the temporal component and negative signs and the spatial components, right? So that is the end of chapter 2. What we're going to go into now is fields. And fields are, this is where things get really interesting. We're going to be able to generalize. We're going to be able to talk about spinners. And we're going to be able to talk about, you know, vector fields, spinor fields, and scalar fields, and everything's going to sort of build up from there. We're going to understand, we're going to try to answer the question, why a field? Why are fields so important in this type of theory? And we're going to go from there. Again, if you guys are interested in my channel, my Patreon page is a little bit, has been a little bit unused for a while, and so I'm going to try to revamp things up on my Patreon page. But what you'll be able to do on that page is, if you contribute, you'll be able to request books, you'll be able to request topics, you'll be able to do that kind of stuff. And if you make a contribution to this channel, if you don't make contributions, I'm still going to make content, right? I'm still going to want to make content. It's just going to be at my leisure. If you have any specific requests, any specific books that you would like me to go over, anything really, I plan on going over literally everything in science, because all of this interests me, and I've been studying this kind of stuff for a really, really long time. If you want to do that, you feel free. I will make an announcement when the Patreon page is fixed up and ready to go. And yeah, so I'll see you guys in the next one. Thanks.